We have talked about the strength of an acid. A strong acid is an acid that is mostly displaced to products. A weak acid is an acid that is not all displaced into products, that there is an equilibrium between reactants and products. Now let's try to study what we already know qualitatively from the quantitative point of view. Now we're going to define an equilibrium constant in which an acid dissociates in water. That is called Ka. The Ka is just like not any other regular equilibrium constant, just that it already refers to the equilibrium constant of an acid dissociating in water. So a strong acid will have a Ka much larger than 1. Remember that Ka is, or any equilibrium constant, is the concentration of products over the concentration of reactants. In this case, however, notice that we are not writing the concentration of water because it's a pure liquid. Its concentration is around 55 molar, much larger than anything else that we're going to be dealing with. It's considered a constant. We do not write it explicitly in the equilibrium constant expression. So a strong acid will have pretty much a lot of ions because it's all displaced to the right. However, a weak acid will have less amount of ions. So it will conduct, in terms of electrolytes, it will conduct less the electricity. This is why the light bulb is more dim. It's not as bright as if what you're throwing in here is a strong electrolyte, such as a strong acid. Again, notice that the equilibrium constant is always products over reactants. A Ka will always have the concentration of H3O plus in the numerator and the conjugate base also in the numerator. We will also define Kb if you have a base reacting in water. I'm just writing it here so that you see it for completion. A base dissociated in water will have a Kb in which the expression is, again, products over reactants. And notice that as a difference from the Ka, a Kb has explicitly the concentration of OH negative. However, a Ka has the concentration of H3O plus. Needless to say that the stronger acid will have a larger Ka and therefore a higher concentration of hydronium ions in solution. A smaller Ka will be a weaker acid and it will have a lower concentration of H3O+. What is the range of a strong acid or a weak acid? Typically, if a Ka is much larger than 1, we will talk about the strong acid. If this is much smaller than 1, we will talk about a weak acid. So if the Ka is around 1, we will still be talking about strong acid. Let me remind you, hydrogen sulfate has a Ka around 10 to the negative 1. So we still consider this a strong acid. So careful, because this one is in no man's land, if you will, between the very strong acids and the much weaker acids. We will still call this guy a strong acid because the Ka is around, not quite equal to 1, but around 1. Okay, so let's do some calculations here. In this case, we want to know the concentration of hydronium ions and hydroxides of a solution of acetic acid 0.5 molar. And it's giving you the Ka. Notice the Ka is fairly small, so expect these kind of numbers when we talk about weak acids. So let's see. Initially, I have 0.5 molar. I'm not going to talk about concentration of water because it's constant. And you would say, well, it's going to be 10 to the negative 7 most of the times, because in pure water you have initially 10 to the negative 7 molar. But most of the times we'll consider, you know what, this is going to be pretty much 0. We're going to assume that it does not change the final result. So the change that you'll see is there's negative x, there's plus x, and there's x. So in equilibrium you have 0.5, negative x, x, and x. The Ka expression is concentration of H3O plus, concentration of acetate over concentration of acetic acid. Or in terms of x, you have x times x, 0.5 minus X, and this is equal to 1.5 times 10 to the negative 5. That's the Ka. Now notice that this Ka is very small, therefore X will be very small. We can approximate the denominator pretty much as if it were just 0.5. This is going to simplify our calculations because now I just have this 1.8 times 10 to the negative 5. Therefore X will be the root square of 1.5 times 10 to the negative 5 times 0.5. This is the concentration of H3O plus, which is also the concentration in equilibrium of acetate. Okay, the concentration of OH negative, even though this is not a base, because there's some hydronium being created, it will change, and it's always this. It's related to the concentration of hydronium. So this will be 10 to the negative 14, and the concentration of hydronium is this value, which we call X. So there you go. We can find the concentration of hydroxides and the concentrations of hydronium in solution, in this case, for an acid reaction. In the next video, we will solve the same for a basic reaction and for a neutral reaction.